Guys, we're continuing what we started last week, where we were calculating the equilibrium concentrations of reactants and products in a reversible reaction given initial conditions only. We're going to do a problem today that's a little bit more difficult than the one that we started on Friday. In this one, hydrogen gas and chlorine, also a gas, go to make hydrogen chloride, also a gas. So I think one of the things that I'm missing here that I probably should have in place are phase labels. Everything's a gas, and that's important when we set up our equilibrium expression. The two initial values or concentrations that are given to us are for hydrogen gas and for chlorine gas. I want to look for that little subscript 0 that tells me that's the initial concentration. I should also note that when something isn't given, we can assume that it's 0. So in this particular case, HCl is not given to us. We'll assume that its initial value is 0. The other thing that's given that I haven't written down yet is the value of K. And for this reaction, the value of K is equal to 20. Again, no units on that. And so as we did last time, we're going to set up what's called an ice table. And the ice table starts with our initial conditions, which are given. 1.00 molar for chlorine, does need to be a molarity. 2.00 molar for chlorine. I said 1 for chlorine, but that was for hydrogen. And 0 for HCl. The change in conditions, we know the reaction is going to go to the right initially before it reaches equilibrium. We know that because we don't have any product at all, so the reverse reaction is impossible, at least initially. And so in the change, what we need to look at are coefficients. And so, for instance, I know some amount of hydrogen gas is going to react. I'm going to call that minus X. I'm going to lose some portion of my hydrogen gas. But I also know X amount of Cl2 will also react. And the reason I know it's the same is because they are in a 1-to-1 ratio with one another. On the other side, I get plus 2x for HCl. And at equilibrium, my values are just going to be the sum of what I saw in the initial and change conditions. So this will be 1 minus x. This will be 2 minus x. And this will be 2x. Okay? So I'm going to set up now an equilibrium expression. Equilibrium expression can contain gases or aqueous substances. So in this case, it's going to be K is equal to the concentration of my product, HCl, squared because of its coefficient, over the concentration of my two reactants, both to the first power because their coefficient is 1. So I'm going to plug into this equation. This is going to take a lot of space. This is an intense mathematical problem. And so I'm going to change colors just to differentiate, and let's begin. So I'm going to give myself a lot of space. I'm going to write K, which is given to me, is 20. That is equal to 2x all squared over 1 minus x. I'm going to drop the decimal places and remember them later on, but it's just going to make the math a little bit easier. I'm going to put 2 minus x in for Cl2. Now, solving this is pretty intense, and I'm going to try to show several steps along the way. so that everybody can follow. And I'm going to go pretty slowly so that everybody has a chance to write everything down. But pause if you need to, because there's a lot coming. So the first of many steps, 20 equals. On the right side, I need to square 2x. I got to be careful there. It's not 2x squared, it's 2x all squared. And so this is going to be in the numerator 4x squared. And then on the bottom, I'm going to distribute, I think that's the right word. And here's what I get. I get 2 minus x minus 2x plus x squared. Now, let's combine those x terms. So essentially, I get 20 equals 4x squared over 2 minus 3x plus x squared. Now I'm going to cross multiply, and you think of it this way. This is a 1 on the bottom. So when I cross multiply and distribute, what I end up with is as follows. 40 minus 60x plus 20x squared equals 4x squared. I want to group terms together. So I'm going to bring the 4x squared to the other side. I'm also going to align this with kind of the traditional polynomial format. And so when I bring 4x to the other side and subtract it from 20x squared, I get 16x squared minus 60x plus 40 equals 0. I'm going to rewrite that. So those of you who are in Algebra 2 are familiar with the way to go about solving this problem from here on out. We need to use the quadratic formula to do that. And I know there are a handful of students that may not have been exposed to the quadratic formula. That's okay. I'm going to teach it to you right now, and I think it's going to go pretty well. Essentially, in the quadratic formula, as many of you know, each coefficient is labeled a particular letter. So this is A, this is B, and this is C. Or if I wanted to, I could rewrite it as just A equals 16, B equals negative 60, and C equals 40. And the quadratic formula says if we want to solve this, here's what we have to do. We have to take the negative of B plus or minus the square root of B squared minus 4AC over 2A. It's going to give us two potential answers. We'll have to decide which one's the right one. So if I plug in everything, my B value is negative 60. So if I take the negative of negative 60, I get 60 plus or minus the square root of B squared. I'm going to go ahead and do that math because I'm running out of room. B squared is negative 60 squared. That's 3,600. Minus 4AC. That's 4 times 16 times 40. That comes out to 2,560. I'm going to take that over 2A, which is 2 times 16, or 32. We got a lot to do here, but essentially, this is what we're left with. 60 plus or minus square root. Let's simplify here. 3,600 minus 2,560 is 1040. And we're putting that over 32. Let's take the square root of 1040. So we get 60 plus or minus roughly 32.2 divided by 32. This is where we're going to get to two different answers. Okay. So I have two choices now. I can have 60, sorry, I'm moving to the left, plus 32.2, all divided by 32. And if you do the math on this, this comes out to 2.88. Or I can have 60 minus 32.2 over 32. And the math comes out to 0.869. So I have two answers. And in math class, that's where you would be done. But for us chemists, we have to make a choice because we live in reality. And the choice in this case is actually a tough one. I have two positive numbers. Sometimes you'll get a negative value, and you can eliminate that immediately. But in this case, I have two positive answers. So to decide which one is the right answer, here's where I've got to look. I'm going to erase something just so that I have access to some more writing space. I'm going to get rid of that. In order to know which one's the right answer, I have to recognize that at the end of this process, I need to plug back into this equation right here, okay? And I've got to plug in x every single time. Well, look what happens if I plug 2.88 in. Immediately, when I plug 2.88 in, I get 1 minus 2.88. That gives me a negative value, a negative concentration. That'll never happen. So I actually know that this is the wrong answer, and this must be the right one. So I end up with an equilibrium that looks like this. 1 minus 0.869, 2 minus 0.869, and finally 2 times 0.869. So at equilibrium, my concentration of H2 is going to be 0.131 molar. My concentration of Cl2 is going to be 1.13 molar. And my concentration of HCl is going to be 1.74 molar. That took a lot of work. There's nothing easy about solving that type of problem. So what we're going to do is we're going to come back together as a class. We're going to practice one more essentially together as a class. And then I'm going to give you some time to do 2 other examples just so you have enough practice under your belt. Okay, see you back at the meet.